Hello, my name is Gage Sturgeon, and this is my ET350 electric PC motor project. I'm going to start out with my overview. This is a list of all my slides in order, starting from overall diagram exploding view, ball launch video, results, electromagnetic diagram, CAD drawing, construction processes, and experiences, improvements, and takeaways, and then ending off with acknowledgements. So I'm going to start off with my exploded view diagram. And on the right-hand side, you can see my brushed end cap. Oh, all of this is 3D printed except for the magnets. And so the brushed end cap contains a little rectangular recess groove for my brushes to be epoxied in. It allows them to be placed and oriented properly so they don't get misaligned as they're being epoxied. And below that, you can see another little recess for the bearing that holds the shaft. It's the same as the non-brushed end cap, except the non-brushed end cap doesn't have the recess, and the bearing slot is placed on the opposite side. Then next goes our magnet spacers. This allows the magnets to sit inside the stator grooves and be firmly pressed by the non-brushed end cap at all times so they don't move. And the stator has recesses available for the magnets and openings to adjust the brushes and allow power to the brushes to come in and out. Then now we can watch a video of my motor hitting my ball. I'm standing 2 feet away, wearing safety glasses. You'll see this ball get hit, and it'll hit right before this crack over here. So let's take a look. This winds up and hits right here. And I'm gonna play it again so you can see it. Hits right there, right in that little black dot, right here. And play it again. Play it again. And so now we can go to the results. And the total distance was 9.33 feet, which equates to 9.4 inches, and it landed right here, right on this little black dot. Well, there's a bunch of black dots, actually. It's hard to say. But it landed right in this general area. And on the left-hand side, you can see that's 2 foot 6.1 ounces, which equates to 2.375 pounds. The electromagnetic diagrams, we can see both the non-shorted and shorted position of the motor. And so in the non-shorted position, we can see that the brush feeds both the yellow and the red wires, and the red flows back into this unused brush goes to the purple, and the purple goes back to the negative brush, while as so it flows into the yellow now and back to the yellow, into the unused commutation, back in the blue, and the blue flows into the negative brush too. And then we can see the placements of the magnet cause a magnetic flux in this direction. And due to Lorenz's force diagram is seen right here in the top right, it creates counterclockwise rotation. And in the shorted position, we see that both the purple sides have the same magnetic voltage, so there's no current flow. Same with the yellow, so current will flow through the blue and red and back through the current, back to the negative brush on this side. This will cause the similar counterclockwise rotation due to Lorenz's force. And here is an assembly drawing of the whole motor. So we can see that it sits nice and tidy with 4.25 inches in diameter and a total length of 4.99 inches. The actual mounting pieces don't count towards that figure, so I am definitely within bounds. So here is my stator. We can see the canted holes for the all thread to go through. This was specifically designed that way so I can have the placements of my magnets in this particular way. This placement may not have been the best. I'll explain later. We can also see that there's holes in the side to make adjustments to the brushes when it is all assembled, and allow for cords to go to their respective brushes to power the motor. And then now we see our rotor, and it was a total diameter of 2.57 inches, and it has holes to reduce weight. And there were 4 total windings around the whole thing, and they were placed side by side through each hole. And now we can see my brushed end cap. This one has a square recess to hold the brushes and is the opposite from the unbrushed end cap for the bearing recess. And here is a picture of my construction process. Let me move my head real quick so I can see some of this. On the left-hand side, you can see my completed rotor. I did a single pair brush design with a commutator with 12 total pulls, but split into 4 groups of 3 pulls to make a 4-pull commutator design. Here you can see that there's one of the poles. These 3 parts of the commutator are all soldered together, and it has a single wire leading off it. And you can see a little bit on the second to left picture. I am soldering those together and ensuring that they are all magnetically isolated from each other using my multimeter in the picture to the left of that. On the far right, you can see my brush placement in the brushed motor end cap. This is as I'm epoxying it in place, so the recess keeps the brushes in place and prevents them from being misaligned through the curing process. And the second to the right is the completed power supply assembly. So I just used a bunch of butt connectors to safely connect the power cord to the power supply. And then I connected the positive of the power cord to a switch, which is then connected to the power supply to allow the switch to turn the power supply on and off versus the motor. So the actual switch was constructed from 1/2-inch PVC pipe connectors and duct tape to keep it isolated from my fingers to prevent myself from being shocked as I'm using it. And the electrical tape keeps everything kind of sturdy and together, prevents everything from popping out. And at the bottom right, you can see my total assembly before I launched. And you can see that it is firmly mounted to a bunch of wooden pieces and weighed down to ensure it won't fly away. And then the power supply is over here, feeding it power through the back. And then I have a little T underneath the arm to assist in the ball flying as it got hit by the bat. And so let me move my head real quick. My experiences, improvements, and takeaways start with my experiences. I learned to make my own DC motor. It was an extremely incredible event to where I learned a lot how to handle projects from start to finish on the small scale. And I was able to push myself to grow and overcome planning, design, and construction obstacles throughout the project. There's one improvement I would like to have made, and I brought this up earlier about the magnets. I'd like to have more resources available to test how magnet placement affects magnetic flux through the stator of the motor. Because I feel like if I had the ability to see the flux and how it's affected by both the shaft and the other magnets and the all thread around it, I would like to figure out how to place the magnets away from certain things to improve the flux through the motor, which could have greatly improved my efficiency. And the takeaway from this is I have a high understanding for electric DC motors after completing this project. This means I can better apply the fundamentals of Lorentz force, Ampere's law, Faraday's law, Lenz's law, Gauss's law, electricity, and magnetism, and the definition of magnetic flux to other types of electromagnetic machinery. And this is going to be great when I go out into the industry because we are greatly focused on maintaining and installing equipment. This includes motors and diesel generators and other sorts of power hungry equipment that could possibly affect a power plant through power generation or power usage in an electromagnetic manner. And being able to diagnose and keep up with issues is great. And I would love to acknowledge Dr. Ching Su. Thank you very much for assisting me with the project. It was great working with you throughout the years. And finally, thank you to every individual and entity that helped us fund the project. Without you, I would not have been able to try myself and learn as much as I did throughout this semester, especially with COVID. Thank you very much.